Hey, good morning, afternoon, or evening, everybody. Welcome to the Laser Altimetry Applications for a Changing World Working with ICESat-2 Sea Ice Data training webinar. This is your host, Jennifer Brennan. Today's event is the fourth in a multi-part series of ICESat-2 specific data training webinars. And because it is 2 p.m. Eastern Time, let's go ahead and get started here. So what I'd like to do first is begin with some webinar logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A panel rather than the chat, and you should see that on the right side of your screen. If you don't see the Q&A panel, click on the three dots at the bottom of your screen, which should pull up your panel options, and then you can insert a check mark next to the Q&A panel. Today's webinar is being recorded. The recording will be posted online within a week of completion. And then once completed, what I will do on my end is send an email to all registrants and webinar participants that include links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour and 30 minutes long, with 1 hour being allocated to the presentation and live demonstration, and a 15-minute question and answer period to begin after our last speaker has completed her content. Depending on the volume of questions that we receive, we may extend the Q&A session, but we will have a hard cutoff of 3:30 p.m. Eastern Time. During today's webinar, we have 4 speakers. Our first speaker this afternoon is Dr. Amy Neely. Amy is the ICESat-2 Mission Applications Lead here at NASA Goddard Space Flight Center. She's going to kick us off today with some information and an introduction to this ICESat-2 data training webinar series. And then after that, we will transition to our second speaker for this afternoon, Dr. Sarah Qasimi. Dr. Qasimi is a research scientist within the Ocean Circulation and Air-Sea Interaction Group at NASA's Jet Propulsion Laboratory. She will provide an introduction. Let me just actually pull up the agenda as well here. She is going to provide an introduction to sea ice measurements and also the ICESat-2 mission. From there, we will transition to our third speaker this afternoon, Monojit Sajja. Monojit is a graduate research assistant within the Cryospheric Sciences Laboratory at NASA Goddard Space Flight Center. He's going to continue the presentation this afternoon with an in-depth overview of ICESat-2 sea ice data products. After he has finished, we're going to then switch gears to our fourth speaker and to a live demonstration with Dr. Andrew Barrett. Dr. Barrett works as a senior associate scientist at the National Snow and Ice Data Center. He's going to take us through an ICESat-2 sea ice data discovery and data access workflow using earthaccess, which is a Python library. And then once he has finished, Sarah is going to present several sea ice use cases, which will wrap out today's content. And then finally, after that, we're going to transition to our final optional polls and the question and answer period. Before I toss it over to Amy to kick us off, I wanted to just say a couple of words about the Q&A session. We will try to answer all of the questions within the time allotted, but if we're not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, what I'd like to do now is stop sharing my screen and introduce today's first speaker, Amy Neely. Amy, let me go ahead and stop sharing here. Toss it over to you.
Excellent. Thank you, Jennifer.
All right, Amy.
And if y'all can't hear me or see my slides, just let me know.
I see. You'll just need to put it in presenter mode.
Yes. Yep. I haven't gotten there yet. I just wanted to make sure it was functioning. So good to know. Thank you, Jennifer.
I can't hear any audio yet. Amy, I can't hear you.
Okay.
So what you can do is click on the 3 dots. It's going to be your more options. That'll be next to the emoji and hand raising. Oh, you can? I can't hear Amy at all.
Weird.
Hold on a second. Maybe it's on my end.
I was going to say, it seems to be working on my end. Does anybody else not hear me? Oh, they can hear me. Okay, good. It's like it was just working.
I can hear you.
Okay, great.
Delay. Thanks, everybody.
No worries. Thank you for checking, because you never know. All right, I will start this again. So if you can't see my slides, please let me know. Otherwise, I'm gonna proceed. So thank you, Jennifer, for hosting this webinar. And I just want to provide a brief overview of the purpose of these webinars, which this is a multi-part series. So we've already hosted 3 other webinars, and this is the 4th in that series. We have covered an overview of the ICESat-2 mission with a demo of open altimetry. We've talked about vegetation products. We've talked about the bathymetry product, and today we're going to cover sea ice. And we hope to continue these webinars in the future on other topics. And so the purpose of these webinars is threefold. So to highlight the capabilities of ICESat-2, which are multiple, there's many different capabilities and its data products. We want to build the capacity for people to use these data, and we want more people to discover the ICESat-2 data. And in these webinars, we usually have 3 parts, which Jennifer showed in the agenda, which is a data product overview. You have a live tutorial of some sort of tool or code or language to use that data product or visualize that data product. And then we have some examples of how those data products can be used in the real world. So again, today we're touching on sea ice. We are hoping to touch on hydrology in the next webinar, which will be hosted this fall. And we have some openings for other topics to keep this ball rolling. So if folks have any ideas or thoughts or things they want to see covered, please feel free to reach out to me, and I'd be happy to talk about those ideas moving forward. But we want to keep doing this as much as we possibly can. And then these resources are also on the ICESat-2 website, which is linked in the top there. But there's many different resources that are available that folks can use to download, visualize, analyze ICESat-2 data. So I've tried to compile them all here, but they will be in the slides when you are able to download them, and they're also putting the link in the chat. So please feel free to look at all these different ways that you can look at ICESat-2 data. And I just want to thank everyone for coming. And there will be a couple links where you can join the listserv. You can join the newsletter at the links below. And now I am going to toss it over to Dr. Cassini so she can provide some background information about sea ice. Thank you, Dr. Cassini.
Thank you, Amy. So can you see my slides?
Yes.
Yes.
Okay, great. So welcome everyone, and thank you, Amy, for the introduction. If you are attending the webinar today, I suppose that you're either very familiar with sea ice or you might just be curious. So for those who are not very familiar with sea ice, this is what it typically looks like. This is frozen seawater that we can find at the surface of the polar oceans. And this compilation of pictures is there really to highlight how complex and heterogeneous sea ice conditions can be. And we have been monitoring sea ice with remote sensing since the late 70s. And what we know is that in response to increasing temperature, in response to global warming, sea ice coverage or extent has been declining dramatically. And in addition to this decline, we also know that Arctic sea ice is shifting from an older ice cover to a younger ice cover, which is depicted by those 2 panels here on the right. This is the age of the ice as of 1985 on the top and 2021 at the bottom. And so what this means is that the older ice that is typically thick enough to survive the summer is progressively being replaced by a younger seasonal ice cover. And a consequence of that shift is that we expect somewhere around 2050 to have an ice-free summer in the Arctic. So why do we care so much about sea ice and why the sea ice matters for our climate? So there are many reasons, but one of the most important one is probably because of the ice albedo feedback. So sea ice is very reflective. It reflects back to space somewhere between 50 to 70% of the incoming solar radiation. And what this video shows you here is that in areas where we have lost ice, that heat is getting absorbed by the underlying ocean. And so the fact that we're absorbing more heat leads to enhanced melt and further heating. So the ice albedo feedback is really a vicious circle. And so sea ice is critical in the context of climate. And while we know a lot about sea ice coverage and how it has changed over time, in order to better understand what's happening with climate and to improve future predictions, we need more than coverage. We need sea ice thickness, which is an essential climate variable because it helps us better determine changes in heat and freshwater fluxes. But what we also want to know is the sea ice thickness distribution. The time-varying sea ice thickness distribution it integrates the signature of thermodynamic and dynamic processes that drive the decay of the ice cover. So here you have a typical sea ice thickness distribution. We know that the mode of the distribution is associated with thermodynamics, with seasonal growth, whereas the tails are associated with dynamics. So we have thin ice that's formed in leads, which are cracks within the ice cover, and the right tail is associated with convergence and formation of ridges, which happen when ice flows are getting pushed against one another. And so sea ice thickness distribution is really important. But historically, measuring sea ice thickness has been very difficult. And so before the turn of our century, the most comprehensive compilation of sea ice thickness measurements were provided by measurements from ships and also upward-looking sonars on submarines. You have some examples here on the left panel for the Southern Ocean and for the Central Arctic. And while these estimates are very useful, they only provide a limited view of how ice thickness is changing over time. So what really transformed our understanding of sea ice thickness is the ability to derive it from altimetry for the first time using observations from radar altimeter missions, ARS-1 and ARS-2. And this was done by Seymour Laxon, and you can see an example of the winter Arctic ice thickness for several years here on the right. But since ARS-1 and ARS-2, we've had 3 dedicated polar altimetry missions. So we've had ICESat, which is the predecessor of ICESat-2, which operated between 2003 and 2009. And ICESat is unique because it's actually the very first Earth-focused LiDAR altimetry mission. The second one, CRYSat-2, is an ESA mission, and it carries a radar altimeter, and CRYSat-2 is still operating. And CRYSat-2 was the first cryosphere-dedicated radar altimetry mission. And finally, the last one that we'll talk a lot about today is ICESat-2, the follow-on to ICESat, a NASA mission launched in 2018. And ICESat-2 is very unique because it carries the first photon-counting LiDAR. And this technology is a significant advance because photon-counting technology enables us to time tag each of the photon and sample the surface of the ice at a very high resolution. So ICESat-2 operates at a wavelength of 530 nanometers, and it samples the surface using 3 pairs of beams, one strong and one weak. And those pairs are separated by a distance of 3.3 kilometers. And over sea ice, we do have a variable along track resolution, and Monojit is going to give you a lot more details about that in a minute. And early results showed that the precision that we get with ICESat over sea ice is in the order of a couple centimeters. So with that, I will toss it to Monojit.
Thank you so much, Dr. Kasimi. So it's a pleasure. So basically, what I'll try to do, starting from here, is following up from the introduction that Dr. Kasimi presented. I'd like to talk a bit more about the current sea ice data products that are currently available from ICESat-2. So primarily, as we know, that basically, as of now, there are 2 main categories of ICESat-2 data products that are currently available. So one are the along track products, and the second category is the gridded or gridded daily/monthly products. So for the along track product, we have two different products from ICESat-2, which is ATL07, which is the sea ice elevation, and ATL10, which is the sea ice freeboard. And for the gridded monthly products, we have ATL20, which is the gridded sea ice freeboard, and ATL21, which is the gridded sea surface height within sea ice. So I'll go more into the description of these products and what these products actually measure, physically speaking. So following up, when we are working with ICESat-2 data products, one of the primary issues that we all often face is we are downloading an ICESat-2 file. But we also understand that it can be confusing to understand the different product type. But one of the easiest solutions to that is to understand more about the file nomenclature. So as you can see in the slide over here, we have the typical sea ice file format. And as you can see that the file format gives us a range of information, starting from the Atlas product number, i.e. Is it ATL07, ATL10? We can also understand which hemisphere that this is from. Is it the northern hemisphere or the southern hemisphere? We can get an idea about the temporal resolution and also the exact minute or to the second of data acquisition. We can also understand about the reference ground track, which can be used to trace back which particular track you're working with. So a lot of vital information can be obtained when we are working with this ICESat-2 product. Now, moving on, as I talked about the ATL07 and ATL10, I'd like to sort of demonstrate as to what these measurements particularly refer to. So as you can see, we have an idealized sea ice and with snow on top of it. And we also, on the left, you can see we have the open sea ice of open water, which can be used as a reference surface. So as you can see that ICESat-2, basically the 532 nanometer, it interacts with the snow on top of sea ice. And from there, we can get an estimate of what we call the air-snow interface. So it interacts with the top of the snow, and we can use that reference to get an estimate of the sea ice height. And from that, we reference that height based on the WGS84 ellipsoid, which is the standard reference height used in a lot of altimetry products. So following on, we also have ICESat-2 going over the open water. And from there, based on the reference of the open water, we can get an estimate of the sea surface height. And based on that sea surface height of the local sea surface height, we can get an estimate of the freeboard. So the freeboard is essentially the difference between the top of the sea ice and the local water surface. So essentially from ATL10, we are getting an estimate of the freeboard. What is also notable over here is the ATL10, ATL07 sea ice heights are often corrected using several geophysical corrections. And one of those corrections are also the mean sea surface, which is a long-term product or a long-term average of the mean sea surface. And so basically when we are getting some of these corrected ATL07 heights, they are often referred to the mean sea surface. So that is something to note as we work with these products. Now, going a bit more into the ATL07, which is the along track sea ice height. So basically, the ATL07 is generated from an aggregation of ATL03 photon, which is the raw aggregate photons. So basically, using an aggregation of approximately 100 photons, we are trying to get an estimate of the ATL07 sea ice surface. And why 150? It's because of the aggregation, or basically we are trying to sort of understand that to be able to get enough photons to have an segregation between the narrow leads. So the 150 photon counts was good in that respect. So basically what is happening in ATL07 is that as you can see in this diagram over here. So basically, we consider in panel A basically a sea ice and water surface. As you can understand that there are various different types of surface. So based on that, we are getting an estimate of what we call the background count, which is essentially the spectral albedo at 532 nanometers. And as you can see that based on the difference between the surface background count and also the background count, the difference between the water surface and the sea ice surface, we can try to differentiate. Similarly, as you can see in panel D, so basically we can also understand that we can also get quite a difference between the photon or the amount of photon that we are receiving. So based on the difference between the photon rate, we can try to segregate this open water and ice region. We can also notice that in some of these regions, we also get significantly higher photon rates, and even in lead regions, which have significantly higher photon rates, we can get what are called specular returns. So specular returns are where we are getting a significant amount of photon return to us. So based on that, we can also differentiate between leads, between what we're defining as dark leads versus specular leads in this surface. And as panel E also shows that the surface elevation difference between leads versus ice is also a determining factor between this. As you can understand, and based on these properties, what ATL07 essentially does is uses a surface classification decision tree. So based on these three different parameters, what it's essentially trying to do is to segregate between when it is not fully cloud covered, what is the dark lead versus a specular lead versus what we're identifying as ice. So ATL07 gives us this nice classification between these products. Following up, the next product that we are going to talk about is the ATL10 along track sea ice freeboard. Now, it is a follow-up from the ATL07 that the surface classification and sea ice height that we got from ATL07. And ATL10, what it essentially does, it uses the lead returns or the open water surface return to estimate a local surface, and based on which we are getting an estimate of the freeboard. Now, what is to note over here is that we saw different type of specular and dark leads in ATL07, but for ATL10, we are only using specular leads. So what is essentially happening in ATL10 is that for approximately the segment of like 10 kilometers, we're trying to aggregate, or we are trying to average out along track the lead or the heights that we're getting from leads. And as you can see that from this surface, from previously, we got a classification of the ATL07 surface classification. So in this diagram, you see that we have ice in blue, the dark leads are in red, and in green, we have the specular leads. Now, idealizing that, okay, this is one 10-kilometer segment, we get an estimate of the ATL07 height, and based on a maximum threshold or Emax that is set in the ATL07 product, we can get an average of the lead heights that are available. So we get an estimate of the sea surface height, and based on that, we can get the ATL10 freeboard. Please note that this is the along track freeboard, but we can also get an estimate of the swath based freeboard, which would be an aggregate of all the beams in this 10-kilometer segment, which is currently not available in the product, but may be available in the future releases. Now, following up, so besides the along track products, we also have the gridded daily and monthly products. So ATL20 is the gridded daily and monthly sea ice product. And the key features of this is that using the ATL10 along track product, this is sort of like an aggregation based on daily and monthly categories. And what's essentially happening over here is that the aggregation is being done in a 25-kilometer grid, which is projected in NSIDC Northern Polar Stereographic Projection. which is ultimately giving us a nice estimate or a regional estimate of these products, which is very helpful for pan-Arctic studies and overall getting a picture of what is happening in the overall Arctic. Similarly, we also have the ATL21 product, which is basically a gridded daily and monthly sea surface height in ice-covered regions. So basically, it's also derived from the ATL10 lead segments that we are in open water. And similar to ATL20, it is also a 25-kilometer daily and month grid cell with a daily and monthly resolution. The ATL21 also has various oceanographic applications, including measuring sea ice variability, sea level variability underneath the ice. So following up, so basically, this is a video, and this is the sea ice thickness measured from derived products from Alec Petit et al. So basically, what is happening over here is from ICESat-2, we are not directly measuring sea ice thickness, but we are getting a measurement of the sea ice freeboard, as you have seen in ATL10. So using that and using estimates of different models, such as NESOSIM and other models, snow depth and snow density measurements, we are trying to get sea ice thickness, which Dr. Kasimi will go into more in the future slides. So basically, the overall idea is from ICESat-2, we can get indirect measurements of sea ice thickness, which is considered a very important factor or variable for our changing Arctic. So I'll pass it on to Dr. Andy Barrett, who will show you a bit more about how to access the product and how to really get hands-on with the product. So, thank you.
So thank you, Manojit. Thank you, Dr. Kasimi. I am going to now show you how to access some of this data that we've been highlighting in this webinar and in other webinars within this series. And I have 4 learning objectives, or 4 things I want to demonstrate to you. 1 and 2, how to search for ICESat-2 datasets using the Python earthaccess library. 2 is search for data files using that same library, and then show you how to open and work with the ATL07 product using another Python library called XArray and some plotting functionality there. I'm also going to be using the Pandas library. These are, I'll introduce these tools in a little bit more detail. But the idea behind earthaccess is to allow you to search for and access data within a Python script or Python notebook, which is especially useful if you're in the cloud. But these workflows work both within the cloud and on your local machine. So a little bit about the tools. earthaccess is a community-supported open-source Python package for programmatic search and access of any NASA data that's available. So if you're familiar with Earthdata Search, which is the web interface, then you can do essentially the same things using earthaccess as you would want to do with Earthdata Search, but it allows you to script it, which is important for reproducibility. And it was created initially as part of the NASA OpenScapes program by Luis Lopez, one of the developers at NSIDC, to take the pain out of data access, both in the cloud and from a local machine. As we were teaching tutorials about the transition to the cloud, a lot of users were finding access and in particular authentication difficult. And so we wrote this package to help. And it gets you to doing science quicker. You can search for and access NASA data in as little as 3 lines of code. And joking aside, it could quite possibly improve your life. It streamlines scientific workflow as well. I'm also going to be using X-ray and pandas. X-ray is, I think, the go-to package for Earth data science. Is developed for multi-dimensional data sets like NetCDF4 and HDF5. And an improvement as of version 2024-10 is that X-ray can now handle hierarchical file formats such as HDF5, which is what most of the ICESat-2 data are in. I'm also going to use pandas. It's a widely used data science tool for table-like data. And if you need an image for table-like data, it's the kind of data that you work with in spreadsheet programs like Excel. And it's well suited to working with vector or trajectory data, such as ICESat-2 along track data. Now, I'm going to be live coding this, but I have a more documented version of this tutorial at this link here, and I think Jennifer has just shared this with you in the chat. So feel free to go to NSIDC Data Tutorials and check out the tutorial there. So with any Python workflows, I'm working in a notebook, Jupyter notebook, but if you were scripting this or even working from the command line, the first thing you have to do is to import your tools. So I'm going to import earthaccess. I'm going to import X-ray, and I'm going to give it a short name. It's kind of the standard short name that we give X-ray XR. Just saves typing, and I'm going to import pandas, and again, give it a short name of PD. This is pretty standard within work with pandas and X-ray. So the next step we need to do, and this is really the genius of earthaccess, is that we need to authenticate. You need to access any NASA data, you need an Earthdata login, and you need to provide that Earthdata login as well when you're downloading data on the cloud from a script. You also need authentication to access the Amazon Web Services cloud that the NASA data is stored in. You don't have to think about this. earthaccess deals with it. All you need to do is to go and register for an Earthdata login if you haven't already done that. I have the link for that in the documented part of this tutorial. And we just issue a very simple command, earthaccess login. Now, I have this set up using what is called a netrc file, so that I don't have to expose my credentials to anyone. But if earthaccess doesn't find that netrc file or one of the other authentication tools, it will prompt you for your Earthdata login and password, so you can enter those within the spreadsheet. Just be secure and don't publish that to anyone. Don't share your credentials. So there we go. We're authenticated. And you don't actually need to do this to search for data. You do need to do it for access, but I like to do it up front so that I don't forget and get to the point where I'm trying to download data and have to authenticate. So the next step is let's search for some data sets. We need information about data sets. We need to know what those data sets are called and what's available. So I'm going to use a method called search datasets. And I'm going to assume that I don't know what those datasets are or what's available. So I'm just going to do a keyword search for any dataset that refers to ICESat-2 or comes from the platform from ICESat-2. I want to also refine that a little bit. So let's say I want to work with the data, so I want it to be downloadable. And I'm only going to be interested in cloud-hosted data. Almost all, I think, in fact, all ICESat-2 data, the standard products are in the cloud now, so you wouldn't necessarily need to do this, but I also want to avoid returning a bunch of data that hasn't yet been migrated to the cloud. And that goes off. It searches the NASA data archive, called CMR, looking for NASA data set. So it's finished. The little square brackets on the edge have turned from an asterisk to a number. And let's find out how much or how many data sets we've got. Search datasets actually returns a list of data collections, a Python list, and we can find the number of collections just by getting the length of that list, the number of elements in results. And we have 47 data sets here that we've got. So, as I said, this is a list of collections, and we can find some information about any one of those collections by using the summary method, and that gives us some information about what that collection is and how to access it. So it gives a short name. We're going to be using that to actually search for data granules. Those are the actual files that have the data in them. There's also a concept ID. This is a unique identifier used by the NASA data centers to identify data sets. We can use that instead of the short name, but most ICESat-2, in fact, all ICESat-2 data has this nice ATL and then the number of the data set. So the short name's easier to remember. There's also a version. This is version 6. NASA keeps the last 2 versions. Current version of ICESat-2 for most data sets is 7. So we've got 6 and 7 here. And then there's information about file type and then a set of links on how to get the data. Right. So that tells us about the first data collection, but what about the rest? And here I'm going to use I'm going to just go through this list of data sets and print out the results. So I want those sorted because it's a little easier to read. And I'm going to use this summary command again. And I want the short name. And I want to know the version. So this is using what's called a list comprehension. You can think of it as a for loop, but what it does is to go through each of the elements in results and does what we ask it to do here in here, which is get the version and short name from the summary. I want to, as I said, I want to sort that, and I want to sort it on the short name. And I'm just going to use a little bit of Python magic here, a lambda function, and tell it that what I want is to sort it based on the first element of this thing called X. Well, this here is X, and the first element of X is the short name. So we're going to search or sort on the short name, and we've got a spelling mistake here. So let's just correct that. And here you go. You can see that we have, these are the 47 data sets that we found. We can see a lot of ICESat-2 standard products, version 6 and 7, goes from 2, 3, 4, all the way through. There's some quick look versions here. These are rapidly processed data that haven't been quality checked yet, but that they're available for use in more operational standards or processes, all the way through to data sets down to 23, 24. And there's a few other data sets in here that aren't standard products, but use the ICESat-2 data from the platform. We're going to be interested in, as Manjit highlighted, in the ATL07 data and the ATL10 data. And I'm going to focus on ATL7 now. So let's try and get some data. Well, again, we just use a very similar pattern to we did for searching for the data sets. We're going to use search, but this time we're going to use search data. And this is searching for what NASA calls data granules, but you can think of those as the data files. And we want to get the ATL07, and we're going to tell it that we want the short name. We want, and if we just did short name, we'd get the whole, all the ATL07 data that's available since launch. So we want to restrict it by time, and for that we use the temporal method. And I know that there's data that was collected on the 26th of July in 2022 that was part of the CIS validation campaign. So I'm going to get those data. And here, because I'm just focused on a single day, I'm just going to add the same dates in for both parts of the argument past to temporal, but this could be any date range you want in this international format. And then we're going to restrict it to version 6, sorry. Now, it shows that version 7 is available, but in fact, version 7 has been halted. The processing has been halted to deal with some issues. So at the moment, the only data that is available is version 6. And yes, set that running. Again, it's going off and searching CMR to look for granules. And we can use the same length method to get the number of granules, and there's 31. And again, we can print or look at one of these. Now, here, if I just say granules and the index of the first element in there, I get a nice little rendering of what that data is. So I get the file name, I get the size, and I get these two little displays of the actual data and where that data is. And if I do print granules, I get a text representation with a little more detail. Again, still where to get data from, but some information about the spatial coverage, the temporal coverage, and the fact that this is sea ice height data. Now, there are a number of different or other ways that we can search for this data, or tools that we can use for searching. We can use a bounding box, and I'm just going to copy this because I'm going to repeat the same type of search, but I'm going to say I'm just interested in data for the Northern Hemisphere Arctic region. And we So we got half the data back because it was looking at only half the site. Now we can also just search by granule name, which is kind of helpful, especially if you're just trying to reproduce some some workflow or a paper or something like that. And here, because I know this is a short list, I'm just going to check that we got this data here. So we found some ATL07 data. I knew I was interested in this reference ground track number, which is a way to identify your ICESat-2 data. This is 531, and Manji kind of explained how this file name is broken down. So we know this data exists. We know where it is. We want to get it, and we can just say download the data. And just to keep my directory structure simple and clean, I'm going to tell it where I want to store it. The default is it stores it in the directory you're working in. I want to have a data directory. That's where I'm going to store it. And this ran fast because I already have that data downloaded. So earthaccess actually checks to see if you have that data on your file system and doesn't download it if you want. There's another method we can use, which is called open, and that is useful when you're working in the cloud because it allows you to open into memory. Now, we can look at files, and that's just a path to where your data is. So we've gone through the steps. Those are the three simple commands of authenticating, searching for data, and downloading data. Let's open it. And I'm going to use Xarray to do this. And I'm going to use Xarray's open data tree. And we can just tell it we want to look in files. And I'm going to add this keyword, decode time delta equals true, because if I don't, Xarray throws a warning, and this is the way that it says to get around having that warning. It doesn't affect the processing. It's just telling me that in the future, we're going to need to specify time date. And what do we got here? We've got another warning. Okay, so this is telling me that I don't have things set up right. In the interest of time, I'm going to switch to one that I prepared earlier and just talk you through what we have here. So this is the dangers of live demonstrations. So what I'm scrolling through here, we've opened the data tree, and now we're looking at this structure, and this allows you to actually start exploring what's in the file and looking at the groups. The ICESat-2 data's HDF5 is a hierarchical data structure, which means it has these nested, you can think of it as a nested directory structure where your data is. And you can use Xarray's rendering here to explore what's in the groups. You can see we've got the beams here, Grand Track to right, with this is the geolocation data, and you've got geophysical corrections, and height segments and data. So you can use this to explore the data. One critical piece of information you need to know is what the orientation of the satellite was. Depending on which orientation the satellite's in, beams switch from being weak beams to strong beams. This is for the forward direction. This is for the backward direction. And so you can see that Grand Track 1 in the forward direction is weak. It's strong in the backward direction. We're going to focus on Grand Track 1R. You can find out what that orientation is from the SC orient variable. And you can find out about that here, and even find out where to look in the algorithm theoretical basis document. Knowing that, I'm going to select Grand Track 1R, And I'm going to create a pandas data frame using CI segments. And I'm going to load the along track distance, which is the distance of each CI segment from the equator, the heights, latitude, just because I want to know, at least in geographical coordinates, where it is, CI's height flag, the segment type, which is the surface type of that segment, which Manojit showed a figure of that. And then there's also some quality information here. I'm really going to focus on just the heights, the segment distance, and the type. When we load it into pandas, we're taking it from the data tree object and getting these variables, and it creates a nice table. And that allows us to very easily create a plot. Now, here I'm just using the pandas data frame plot, scatter plot tool, where I say I want to plot distance, I want to plot height, and then I want to color my dots that I plot on the map by surface type. And I use this color map, which I've loaded with 4 different colors for different surface types: cloud, snow and ice, specular lead, and dark lead. And then I've set up a boundary, a normalization, a way to map the surface type to a color by just setting the bounds based on information I got from the attribute. So cloud is 0, snow and ice is 1. Specular leads, those are the ones that are used for determining sea ice height. Oh, it's the sea surface height, 2 to 5, dark leads 6 to 9. And by doing that, we can generate a plot very similar to the one that Manojit showed here with a legend and different colors. So I'll stop there. Go check out the rest of the tutorial. I show some other ways of accessing data, searching for the data, different commands within earthaccess that you can use. I hope that was useful. So I'll stop sharing and hand back to Dr. Kasumi for applications.
Thank you, Dr. Barrett. I will move on with use cases. Okay, so in the next few slides, I will give you an overview of some different ways in which we can use the ICESat-2 CIS data products for different applications. And by no means, this is not an exhaustive list. So, there's a lot more that we can do with those products. So the first one, obviously, as Manojit introduced earlier, is CIS thickness. The motivation to get CIS Freeboard in the first place is so we can get to the ice thickness. And the way that is by assuming that an ice flow is in hydrostatic equilibrium, meaning that it is balanced by buoyancy forces and gravity. But so what we measure with the altimetry is the freeboard. This is one of the prerequisites to get the ice thickness, but there are also other parameters that we need. And it includes the density of water, ice, and snow, and also the snow depth. So for some of those parameters, we do have a good sense of what the value should be, but snow density and snow depth are still very difficult to get accurately, just because our knowledge of the spatial and temporal variability of snow density and snow depth is more limited. And so typically, the way that we have prescribed for many years snow depth for retrieval of ice thickness from altimetry is by using a snow climatology. And you have an example here displayed on the map on the left. And this climatology was derived from using data from drifting from Soviet station deployed on Arctic sea ice between the 50s and the 90s. And while the climatology has been really useful, it is somehow dated because since then Arctic sea ice has undergone a lot of changes. We also have estimates of snow depth from field measurements. You see some examples here on the left. So these are tracks from Operation Icebridge surveys and also from buoys, which are depicted by the triangles. And those estimates are very reliable, but limited in terms of their spatial sampling. So another common way that we prescribe snow depth is by using a model. And this is actually for the result, for the video that Monojit showed you, this is the snow depth that we use. It is produced by a model called NESOSIM. And here on the right, you have a diagram that summarizes the information that gets into constructing a snow field. So it is based on observations of sea ice concentration, sea ice drift, and also snowfall from reanalysis. So the way that it works is at the beginning of the growth season, we start accumulating snow on a parcel of ice that is advected. And for that specific model, we also have loss terms that are written in red. So we do have snow that is lost due to wind and just snowfall that is falling into the ocean. So that's a way that we can get daily estimates of snow depth. But that leads me to my second use case, which is really exciting, and the ability to derive snow depth from altimetry directly. I forgot to mention that for these specific use cases, the name of the ICESat-2 data product that is relevant is written here, and the name of the people working on each use case should be written in light blue. So snow depth from altimetry, the concept is very simple. Here, what you're looking at is a diagram similar to what Monojit showed earlier. So this is a schematic representation of two ice flows separated by a lead. And what we measure in a lead is the sea surface height or the sea surface height anomaly if it's referenced to the mean sea surface. And then above an ice flow, we measure with ICESat-2 what we call the total freeboard, meaning that it's the snow and ice above the waterline. But with CryoSat-2, and this is a mission that I briefly touched upon earlier, it's an ESA mission that carries a KU band radar altimeter. At this frequency, we can theoretically penetrate all the way to the snow-ice interface. So really, the ability to derive snow depth from altimetry is something that was brought by the synergy of ICESat-2 and CryoSat-2. So getting an estimate, knowing the different penetration depth of ICESat-2 and CryoSat-2, we know that the snow depth is just can be derived by taking the difference between the freeboards. And so if you do that and combine ICESat-2 and CryoSat-2 observations that are not exactly coincident in space and time, you can end up with those large-scale estimates of snow depth. And this video here loops through one Arctic growth season, so from October to April. And from left to right, those images shows you 3 consecutive growth seasons. And so what we can see is that by applying this technique, the snowfields that we end up with are consistent with what we know of the Arctic snow cover. For example, we see this gradient that we expect between Canada and Siberia. But what's really great in comparison to, let's say, the climatology is that we do capture an interannual variability. So this is a really, really cool use case that actually motivated there you go. That actually motivated the Cryo2Ice campaign. If you're not familiar with it, the Cryo2Ice campaign is a campaign that in which CryoSat-2 orbits were slightly shifted to periodically align with ICESat-2 observations and to enable near coincident data. And the motivation behind it was really one of the most important motivation was the ability to retrieve snow depth using both satellites. And a lot of people have used these data sets to look at snow depth, including Monojit, who's used the Cryo2Ice data over landfast ice. And this example is from Chris Picard. And he has looked at ICESat-2 and CryoSat-2 freeboard and the retrieved snow depth that you can see here on the right over the Fram Strait. And the Fram Strait is an area of significant interest because it is a major pathway for sea ice export. And the sea ice there is slightly different from the one in the Arctic Ocean because, it's a very dynamic area. So, with Cryo2Ice and ICESat-2 and CryoSat-2, there are lots of new data sets and applications that are coming with the synergy of those 2 satellite missions. Now, another use case that is really exciting and actually will be included in the next beta release of ATL07 data is the possibility to get some information on melt ponds. So If you're not familiar with melt ponds, they are pools of open water at the surface of sea ice, and they're very characteristic of Arctic sea ice. And you have some pictures here on the top. And beyond being beautiful, the reason why we care about melt ponds, it's because they have a lower albedo than the surrounding ice. This is what you can see here on the left. This is the albedo variability as a function of wavelength for different surface types. And these are based on field data acquired during the Mosaic expedition. And as you can see, the purple and magenta lines, which correspond to ponds, are all have lower albedos than other surface types. We also know from field measurements that melt ponds are associated with a significant change in ice albedo during the summer. So melt ponds are important because they can be determining for the end of summer ice conditions, and because they absorb a lot of heat and contribute to enhanced melt. But monitoring, getting more information about melt ponds characteristics has been really difficult using remote sensing. But recent work done by Ute Hersfeld and Thomas Tenfro and others, enables now the better characterization of melt ponds. And so the way that they do this is by using the DDA algorithm, so the density dimension algorithm, which enables the tracking of different returns at the same location, so the top and the bottom of the pond. And here on the right, you have an example. This is an image that was taken during the 2022 summer ICESat-2 campaign. And you can see that we have different options for the retrieval of the depth of the pond. And so this information and the results of this algorithm, the DDA, will be included in the ICESat-2 Release 7, which is getting produced at the moment. So another use case is polar oceans, because as much as ICESat-2 over sea ice, we can get information about the sea ice cover. We can also get information about the underlying ocean. And historically, satellite altimetry has been used to monitor the open ocean, so changes in sea level and ocean circulation. Now we can do the same over the polar oceans, but we have to look under the ice. And so this figure here shows you the seasonal mean sea surface height anomalies from 2018 to 2020, and that we get from leads, returns from the leads. And here on the right, this is, I don't know if you're familiar with what the Hov-Moller diagram is, but on the vertical axis, this is the temporal dimension. And the horizontal axis shows you the distance from the coast. And here, this is a comparison of the coastal sea surface height anomaly variability that we get from ICESat-2 on the left and from an ocean numerical model on the right for a specific region here depicted by this box. So with ICESat-2 sea ice data, you can get some information about, the variability of the underlying ocean. Another thing that is of significant interest is sea ice leads. And so sea ice leads are important because they're areas of active exchange of heat and moisture between the atmosphere and the ocean. And also because sea ice leads allow light to penetrate into the water. They support ecosystem and specifically the formation of phytoplankton blooms. So sea ice leads are, scientifically interesting. Also, we know that climate models cannot resolve leads. So getting a better representation characterization of those sea ice leads is important to help inform those models. And here, what we're looking at is the winter lead fraction that we get between 2018 and 2024 using different ICESat-2 sea ice data products, so ATL07 and ATL10. And what is really the advantage of ICESat-2 is that we can have a very high resolution and near pond Arctic coverage, because as Monojit mentioned earlier, we do have a long track resolution that changes and adapts according to the surface reflectance. So if you have a very specular return, very bright lead, then you're going to have a very small segment length, for long track segment length. And so with ICESat-2, we can identify narrow leads in comparison to traditional radar altimetry. And my final use case is, beyond what we can observe with ICESat-2, how can we use those observations to inform models? And so in that case, what you're looking at is a comparison of the snow depth that we get by combining ICESat-2 and CryoSat-2 observations and the NESOSIM model that I introduced earlier. And I'm not going to get into the detail of these differences, but this is just to show that, intercomparisons between models and observations can really help us pinpoint potential deficiencies in the model. So we know that in the model, maybe if we were to tweak the snow accumulation or, loss term, maybe we could get a better agreement with the observation. So those intercomparisons are really important to help improve models. Another example is how we can inform ocean models. So here in this example, I'm showing the ECHO model. Some of you might be familiar with. This is an ocean state model that integrates, a numerical ocean model, but also observations from satellite and in situ observations from, for example, from moorings and instrumented seals. And ECHO does have a sea ice component. And so in that case, the comparison of ICESat-2 total freeboard, which is the top row here, with ECHO is informative. So what you are seeing here, the ICESat-2 curve is the blue one and the ECHO is the green one. And you can see that differences in freeboard are also informative in what might cause those differences in the ECHO framework. And so that's work that's being done by Rui Ponte. And that was my last use case. I would like to finish by giving you a very brief update on what you can expect in the next release of sea ice data products. And as I mentioned, we will have more information about tampons because of the inclusion of the results from the DDA bifurcation algorithm. We will also introduce some changes in the way that we determine the surface from the photon clouds, because typically the way that we do that is by using a Gaussian feed. And in cases where it performs poorly, then we're going to switch to log normal heights. We'll also make some changes to geophysical correction and to the way that we determine the reference surface height. If you want to know more about this, I encourage you to reach out to Nathan Kurtz, the deputy project scientist of ICESat-2, Jesse Wimmert, and Jeff Lee, who are also involved in the production of these data products. And on that note, I would like to thank you all for listening. The Photon, Paige, the Penguin, and myself and everyone were very happy. And I will toss it back to Jennifer.
Hey, thank you so much, Sarah. So at this point, I'm going to open up the optional final polling questions and then just jump straight into the Q&A here. All right, question is, not long ago, a researcher asked why the coarse resolution for sea ice, since technically ICESat-2 could deliver high resolution gridded product. Do either of you want to weigh in on this?
I can try to answer the question. To be honest, I'm not sure I understand. Maybe, okay. My understanding of the question is, why do we want, if ICESat-2 can deliver very high resolution, why do we bother to have gridded products? And I think that the easy answer to that is because it depends on your application, right? So if you're really interested in getting, fine details about the sea ice surface, then you would want to use a long track product. But then if you want to do if you want to look at large scale changes, then you have to aggregate these data products over certain, time spans and spatial scales. So.
Okay, perfect. Thank you. So the next question is, would you recommend ICESat-2 for monitoring lake ice? If so, which product would you use?
I can answer this one as well. So, lake ice, so there's a product that's being developed right now, and I'm not sure. I think it might already be available, but there's been, extensive work that's been done to provide estimates of lake ice from ICESat-2. So I encourage the person who asked the question to have a look at the available documentation, but I believe there's been some work done to look at lake ice specifically.
Yes, thank you so much, Sarah. And to my backup host, Joseph, if you could place a link to Sarah's slides in the chat again, that would be really helpful. All right, so the next question was responded to with a text response in the Q&A, but I think there's some value in addressing this again verbally for everybody. I don't know, Michaela, if you want to tackle this. So the question or the comment is, earthaccess standalone or with IcePix? What do you recommend? I've been experiencing some bugs while querying in IcePix.
I'm happy to chat about this, and Andy hop in as well. IcePix has been recently updated since the ICESat-2 data have been migrated to the Earthdata Cloud. Some changes have been made to IcePix to adapt to that. And so it's really important to have the most recent version there. IcePix does use earthaccess in some way, which Andy can probably speak to better than I can, but folks often use both of those libraries, some for parts for access and so yeah. Andy, do you want to add anything?
Yeah, I mean, I think you covered most of it. I won't go into the details, but as Michaela said, IcePix has had to change a little bit because of some changes that have happened with the migration of data to the cloud. And so you can do spatial subsetting using IcePix, but you can't yet do variable subsetting, which was something that the earlier versions of IcePix offered. Which to use? I think IcePix does offer a lot more functionality. For some of the other products, it allows you to essentially select a curated set of variables to create your data set, which is useful. As far as I know, I don't think IcePix has yet integrated tools like Xarray's data tree into it. That's something that maybe the team is thinking about. So if you did want to use data tree as I demonstrated, then you might have to use earthaccess or use IcePix and then hand off to Xarray. So I think it depends on your preference. One of the reasons for demonstrating earthaccess is that it allows you to interact with all NASA data sets. IcePix itself is focused on ICESat-2 and some other products such as JEDI, I think. But I think it comes down to your own preference.
Well, perfect. Thank you both for your responses there. Thanks, Andy and Sarah. So it looks like the next questions have been responded to with a text response by Michaela. I'm just scrolling down through here. All right, let me make sure I haven't missed anything. Okay, I see that Michaela's responded to the ICESat-2 long track products question by Sergey. Just scrolling down a bit more. See, and then make sure I haven't missed anything. Thank you, Andy, for responding to the DeepMind query and comment as well. I don't see any questions that I've missed, but let me hop back up to the chat. And while I'm doing that, just to let everybody know as a reminder, again, it'll take a up to a week for webinar post-processing. But today's session will be posted online to a new NASA YouTube channel. If you were following us on NASA Earthdata, that we were part of an agency-wide consolidation effort. And so we'll have a new YouTube channel, and I will send those links out to all registrants and participants within the next week, as well as links to the presentation slide deck and the demonstration that Andy provided. We do have, it looks, Sarah, like you, that you responded to this one as well. Okay, so here is a question. Let's see. Does version 7 have data for summer as well? Maybe I overlooked this, but I've mostly seen data from October through April, so I'm curious if there are data available from May to September.
I can take that question. So ATL7 data is available for year-round. If you have a look, you can download ATL07 data during the summer season. It's just that the ATL10, you still have access to the ATL10. There are just some questions about the validity of the freeboard that we derived during the summer because of the presence of meltdowns. So you should be able to get ATL10 estimates during the summer. And the next data version, 007, which is in production, as I said, will include some information on potential meltdowns.
Okay, thank you very much. All right, I think at this point, if there are no further questions, what we'll do is we will log off from the audio component, but we will leave the virtual meeting space open for an additional 20 minutes or so. So certainly if you have any questions or you think of something for our speakers, please do feel free to jot that into the chat or the Q&A, and they'll be able to follow up with you offline. Also, we really appreciate your feedback for the optional polling questions. It helps us in terms of, taking a look at user needs and also for future data trainings and webinar topics. Let me just take another look. Sometimes there'll be a late breaking question. I don't see any. So with that, I would like to thank all of our speakers this afternoon for their content and for their subject matter expertise, and also my backup host, Joseph Smith, and Michaela Weig from NSIDC for joining as a Q&A panelist. We really appreciate all of your input, and most of all, we really appreciate all of you.